Hello, my name is Yi and I'm a fourth year undergraduate mechanical engineering student at the University of British Columbia. Today, I am presenting my investigation of the cerebrospinal fluid's role in brain injuries through physical and finite element modeling. Currently, a large portion of the advancements in traumatic brain injury research is driven by finite element models. However, most of the models do not accurately represent the cerebrospinal fluid, or CSF, as a fluid. This inaccuracy contributes to the lack of understanding of the effects CSF has on brain tissue deformation during concussion. While physical experiments can incorporate CSF, we do not have a robust method to validate physical and computational models against one another. This project thus attempts to initiate the long-needed research that focuses on accurately representing and replicating CSF and brain interactions through physical and computational methods. The physical modeling side of the project involves inducing rotational acceleration on a cylindrical brain surrogate model using a pendulum and a single-axis turntable. The brain surrogate is made of Stargard 527 silicon and is 5 inches in diameter and height. The CSF is represented by 5 mm thick water surrounding the surrogate brain. The skull is a rigid polycarbonate container. To capture the stream pattern during deformation, tracking markers are masked onto the surrogate brain. We then used digital image correlation analysis, or DIC, to extrapolate strain values. The second part of the project is finite element, or FE modeling. We used a sync waveform with peak acceleration of 3000 radians per second squared and real impact data for the kinematics. The material parameters of the brain surrogate gel are modeled using Oldgam parameters published by Dr. Cliven. 3 different FE models have been created in Elastina. The first one replicates the physical model used for calibrating DIC parameters. The other 2 represent thin 2D slices of the full-scale physical model, one with CSF and one without. The CSF is modeled using the arbitrary Lagrangian Eulerian method in Elastina. Strain results from the physical and FE models are then compared. First, we compare the strain results of the digital image correlation calibration model with the identical finite element replica created in Elastina. The strain values and trends observed from the DIC and the FE model show relatively good agreement. Here we see first principle strain propagate from the edge to the center of the models. With Cliven's material parameters, Elastina models the brain material to be stiffer compared to what DIC has measured. The stiffness discrepancy can be observed in the earlier first principle strain peak and the lower strain values of the FE model. With Elastina parameters validated, the full-scale models are then subjected to the sync wave acceleration up to 3000 radians per second squared. We observed similar strain propagation patterns between the model with and without CSF. Strain develops more axis symmetrically in the model without CSF, with a larger area experiencing the peak strain. However, there was effectively no difference in maximum first principle strain values. Rather, from the time history plot, CSF is shown to delay the peak strain by 4 milliseconds. The strain results from the model with CSF falls within the range of results obtained by previous finite element models and physical experiments. Although different geometries and loading conditions of the models make it difficult to compare models beyond the order of magnitude comparison. Further work with meshes similar to Cliven or McAllister's 3D models may yield subtler discrepancies. In conclusion, we created a pendulum setup for conducting repeatable head impact experiments. We validated a FE model along with published material parameters in Elastina using physical experimentation with DIC analysis. And lastly, from the FE models, we observed that the inclusion of CSF delays the peak first principle strain but does not affect its magnitude. The next steps for this project are to collect data on full-size physical models with and without CSF using DIC, refine DIC and Elastina parameters, and investigate and combine additional boundary conditions such as the existence of Fox and Tentorium. This project was made possible by the NSERC QSRA grant and these supportive labs. Here are the references. Thank you for listening, and I hope to see you at my Q&A session.